Dot product. The dot product v dot w of vectors v equals a1i plus b1j and w equals a2i plus b2j is the sum of the product of the horizontal components and the product of the vertical components. So I see here that v dot w is equal to a1 times a2, which is the product of the horizontal components of the two vectors, plus b1 times b2, which is the product of the vertical components of the two vectors. So this is the definition of the dot product. Let's take a look at an example. So given vectors v equals 2i plus 7j and w equals 12i plus 5j, find v dot w. So what we want to do is we want to find the product of the horizontal components 2 and 12 and add that to the product of the vertical components 7 and 5. So we get that v dot w is equal to 2 times 12 plus 7 times 5, which is 24, 2 times 12, plus 35, 7 times 5. So it turns out that v dot w is just equal to 59. All right, so that is how you find a dot product. Let's take a look at the geometry of the situation. Given vectors 2i plus 7j and 12i plus 5j, which are v and w respectively, find the magnitude of v, the magnitude of w, and the magnitude of vector pq with initial point p equals 2, 7 and terminal point q equals 12, 5. So let's go ahead and find these three magnitudes. First, we'll find the magnitude of vector v. So we'll draw a vector v, which has a horizontal component of 2 and a vertical component of 7. And we'll find the magnitude by taking the square root of the sum of the squares of those two numbers. So the magnitude of vector v is equal to the square root of 2 squared plus the square root of 7 squared, the square of those two components. So that's the square root of 4 plus 49. And 4 plus 49 gives us 53. So the magnitude of vector v is the square root of 53. All right, let's move on to vector w. So vector w has a horizontal component of 12 and a vertical component of 5. So to find the magnitude, it's going to be the square root of 12 squared plus 5 squared. 12 squared is 144, 5 squared is 25. When I add those together, I get 169. So the magnitude of vector w is the square root of 169, which is just 13. So I have that the magnitude of vector w is 13. Lastly, I want the magnitude of vector pq with initial point 27 and terminal point 12, 5. That's basically just a vector with initial point that is the terminal point of vector v, and terminal point that's the terminal point of vector w. So I'm looking for the magnitude of that vector. So I'm going to find the components, and it seems like horizontally the component is going to be 10 units, while vertically the component is going to be negative 2 units. So this vector pq is 10 horizontally, negative 2 vertically. We could have also found that by doing the 12 minus 2 to get the horizontal component and the 5 minus 7 to get the vertical component. We can find the magnitude with these two components. We just have to square both of them, add them together, and take the square root. So I get that the magnitude of vector pq is the square root of 100 plus 4, or the square root of 104. We can simplify the square root of 104 because it has a factor of 4. The square root of 4 times the square root of 26, this can be rewritten as, and the square root of 4 is just 2. So I get that the magnitude of vector pq is equal to 2 square roots of 26, and that is the magnitude of pq. So I now know all three of these lengths. I know that this length is the square root of 53, this length is 2 square roots of 26, and this length is 13. And I'm going to use those lengths and the law of cosines to find the angle theta between the two original vectors v and w. So the law of cosines would say that the square of the side across from the angle is equal to the sum of the squares of the two adjacent sides minus 2 times the product of the length of the two adjacent sides times the cosine of that angle. So we get this. The square of the side across from the angle is equal to the sum of the two adjacent sides squared minus the product of those two times 2. So that's going to be 2 times 13, which is 26, times the square root of 53, times the cosine of that angle theta. So that is the law of cosines. And we're going to go ahead and solve that for theta. So to solve it for theta, I square the square root of 104, which is this. I square the square root of 53 and I square 13. And I get 104, 53, and 169 respectively. I can combine these two, they're like terms. 53 plus 169 is 222. Now to solve for the cosine of theta, I can subtract 222 from both sides of the equal sign. They'll cancel over here, but on the left side I'll get negative 118, which is going to be equal to now negative 26 times the square root of 53 cosine theta. So I'm going to divide both sides by negative 26 times the square root of 53 to get the cosine of theta by itself. And then I can reduce this fraction because 2 goes into both negative 118 and negative 26. Goes into negative 118 59 times, or I should say negative 2 does. And negative 2 goes into negative 26 13 times. So the angle theta I'm looking for is just the arc cosine of that fraction. I get theta is approximately 51 degrees when I round it to the nearest whole degree. There I found the angle theta between vector v and vector w. Let's do this with arbitrary vectors to create a formula for finding the angle between two vectors. Here we have the same situation we just had. We just made the terminal point of vector v arbitrary a1, b1, and the terminal point of vector w arbitrary a2, b2. We're going to look for that angle theta between the two vectors the same way we just did. We're going to start off with the law of cosines. So it's going to be the square of the side across from the angle, which is the magnitude of PQ here, equal the sum of the squares of the two adjacent sides minus 2 times the product of the two adjacent sides magnitudes times the cosine of the angle theta. So this is what we'd get here. This is the law of cosines applied to this oblique triangle created by these vectors. The magnitude of vector v is the square root of a1 squared plus b1 squared, those two components. And likewise, the magnitude of vector w is just the square root of a2 squared plus b2 squared. And the magnitude of vector pq, well, first I have to know the components. To find the components, I have to do a2 minus a1 squared and b2 minus b1 squared. Those are the two horizontal and vertical components, a2 minus a1, b2 minus b1. I square those and I add them together and take the square root to find the magnitude of vector pq. So this will just be the magnitude of the position vector related to vector pq. Okay, so let's plug these expressions in to the law of cosines formula. So I'm going to plug in the component version of the magnitude of vector v here, the component version of the magnitude of vector w here, and the component version of the magnitude of vector pq here. These two magnitude notations I'm going to keep. So I'm plugging in this for the magnitude of pq, and I'm squaring it because of the square. Plugging in this for the magnitude of v, and I'm squaring it. And plugging in this for the magnitude of w, and I'm squaring it. These two I'm going to keep as just the magnitude notation. The squares here are going to cancel the square roots, and we're going to get this. So I get this a2 minus a1 squared plus b2 minus b1 squared is equal to a1 squared plus b1 squared plus a2 squared plus b2 squared minus 2 times the product of the magnitudes times the cosine of theta. So what I'm going to do next is I'm going to FOIL the a2 minus a1 squared and the b2 minus b1 squared. So first outside, inside, last. That's going to give me a2 squared minus 2a1a2 plus a1 squared. When I FOIL this, it's going to be b2 squared minus 2b1b2 plus b1 squared. When I FOIL this, everything else is staying the same. Then I get cancellation. For instance, here I have an a1 squared, here I have an a1 squared, here I have a b1 squared, here I have a b1 squared. And those are going to cancel. Here I have, when I subtract from both sides, here I have an a2 squared, here I have an a2 squared, here I have a b2 squared, here I have a b2 squared. Those are all going to cancel. So all four of these terms are going to cancel with the four identical terms on the other side when you subtract from both sides. And it leaves you with this. And then you're just going to divide every term by -2 to cancel all those -2's. And I get this. So this divided by -2 leaves this. This divided by -2 leaves this. This divided by -2 leaves this. You'll notice that this on the left side is what we defined as the dot product of vector v and vector w. It's the product of the horizontal components added to the product of the vertical components. So the left hand side of this is just v dot w. So we have here another formula for v dot w. V dot w can also be found by taking the magnitude of vector v, multiplying it by the magnitude of vector w, and then multiplying that by the cosine of the angle between the two vectors. So we can use this to find the dot product or the angle between two vectors. Here we're going to use it for the second purpose. Given vector v equals -9i plus 3j and w equals 5i plus 18j, find theta, the angle between vector v and w. So we can use the formula that we just derived to find the angle theta between the two vectors. So on the left side, we'll do the dot product of the two vectors. On the right side, we'll have the magnitude of the two vectors multiply. That'll be multiplied by the cosine of theta. So here we go. The dot product, you take the horizontal components and multiply them and add it to the product of the vertical components. So I get -45 plus 54 on the left side. On the right side, I have the magnitude of vector v, which is the square root of the sum of the two squares, -9 and 3 squared. And the magnitude of w, which is the square root of the sum of the two squared components, 5 squared plus 18 squared. -9 squared is 81, 3 squared is 9, 5 squared is 25, 18 squared is 324. I can combine the like terms on the left side. -45 plus 54 is 9. I can add 81 plus 9 to get 90, 25 plus 324 to get 349. Then I can simplify the square root of 90. That's going to be the square root of 9 times the square root of 10, where the square root of 9 is just 3. And then square root of 10, when I multiply it by 349, I get 3,490. Then I'm going to divide both sides by 3 times 3,490, and I'm going to get this. So the cosine of theta is 3 over the square root of 3,490, which means theta itself is the arc cosine of 3 over 3,490. When I type this into a calculator, I get that theta is approximately 87 degrees. So I use this formula to find the angle theta between the two vectors.